For the next talk with MH Rio from the European Space Agency, who will explain how we get this tricky parameter.
Thank you, Yanis. So, good morning, everyone. Indeed, I will explain you how we can measure ocean surface currents from space. And the first slide try to answer to the question, why do we care? And actually, this was already nicely introduced by Jacqueline earlier. But the main three main reasons is that ocean current, they strongly influence our world climate and weather. Here is a schematic of the thermohaline, or the general 3D ocean circulation, where currents transport the warm water from the equator to the northern latitude when they get colder and denser and they dive at depths, and then are transported back to the southern latitude by deep currents and again rise at the surface and so on. So this is a key reason. Another key reason is that they are key for ocean navigation and transportation, and I will tell more about that in the next slide. And also, as was already mentioned, in transport nutrients, material, energy to different regions and depths of the ocean. So this material can be very helpful as nutrients, eggs, larvae that can be transported across vast distance and ensure the genetic diversity of the ecosystem and population connectivity. But they can also transport harmful material as oil spill, or they transport macroalgae as sargassum, that can beach and be disruptive for human activities. So for those who are not very familiar with ocean currents, this is schematics of the large-scale currents at the surface of the ocean, with intensified currents at the western boundary of the ocean basins, like the Gulf Stream or the Kuroshio current, and then subpolar and subtropical gyres, and then a very strong currents around Antarctica. And I put on the top left schematics of the first map of the Gulf Stream, which was depicted by Benjamin Franklin in 1769. And for the story, at that time, he was a postmaster deputy, and he was asked to explain why the mails which were delivered by ship, they were taking much more time to go from Europe to the America than the contrary, from America to Europe. So by talking with his cousin, who was a whaling captain, he understood that this was due to this large, wide currents that was going from west to east, and which was very known from the fishermen. And so he depicted this first image, this first map of the Gulf Stream, and I will show you now in the next slide that we now have a much better understanding of this current and of the general current. And this is mainly due to one sensor we have on board the altimeter satellites, because actually today we still don't have any satellite mission that provide a direct measurement of current. So we have to use what we have. And the main system that has been used for the last 30 years to estimate current is altimetry. And as we have already heard, altimetry is measuring sea level, actually, and along track. So this is an example of a couple of months of altimeter tracks over the global ocean, and on the right part of the image for the Gulf Stream area. And so we use a very simple approximation, which is called geostrophy. So the ocean is not flat, it has berms and troughs, and when we have you have a particle of water at the top of the hill, it will tend to go down by gravity, but then Earth being rotating, this will be deviated through the Coriolis force to the right to the right in the northern hemisphere, and to the left in the southern hemisphere, and this will create what we call the geostrophic currents. And so when you start from altimetry, so I go back on the right panels, you have the sea level you can use to map by filling the holes using simple methodology. You map the sea level, and then using this simple equation, you get the geostrophic currents. For example, here in the Gulf Stream, you see the velocities from 0 to 2.5 meters per second. And this is to be compared with the schematic I was showing you before. And you can understand that this is very useful for boats navigating and sailors navigating in the ocean to really know where the currents are, which intensity to optimize their route and save fuel and also reduce ship emission. So there are limits, of course, to this system. We have seen that altimetry, they measure the sea level along tracks. And so they are able to see only the large scale and the slow movements of the currents. And this is an example of the tracks, which is superimposed on a map of sea surface temperature at a much higher resolution from a Sentinel-3 satellite. And you can see the warm water in yellow. They are transported by the current, and so you can see the structure of the current, and in that case, a very nice eddy, which is not at all seen by the altimetry because the tracks are on the right and on the left. So when you will map by interpolating the value from the altimeter tracks, you won't see the eddy. So this is the limitation, and there are many work trying to understand how we can fill these gaps. And the most simple idea that can come to your mind is, why don't you use the information that you see in the high resolution temperature? And this is, there are many works looking at how we can do that, so many different techniques. Here I showed just an illustration. It's again in the Sicily Channel in the Mediterranean Sea. You have the altimeter tracks, and what you get when you map the sea level and what you have from a high resolution sea surface temperature with a very small scale filaments and this inverted S shape of the sea surface temperature shaped by the currents. And so when you calculate the geostrophic velocities and you superimposed on the sea surface temperature, you can clearly see that the current cross the temperature structure, so it's not enough short scales. So when you use the temperature to modify the currents, you're able to adjust to correct the altimeter currents and bring more resolution. Another very important point, of course, it has already been mentioned, but we had the launch of the SWOT satellite in December 2022, which is really a game changer for many things, but also for the geostrophic currents. This is an illustration on the right of the classical nadir, we call that, altimeter tracks in the southern ocean, south of Africa. And superimposed, you can see the swath from the SWOT altimeter. So this is a 120 kilometer swath. And within the swath, we are able to map the sea level at 15 to 30 kilometers, and therefore to also access the higher resolution surface currents. So this is an example. You have the pixelized map is from the nadir altimetry mapped, and superimposed you have a swath of the SWOT mission, and you can see the sea level with so this very, very small eddy in the middle of the swath, which is resolved by SWOT, but not by the classical mapping using along track altimetry. And this is a very small eddies that you can see in the temperature in blue, the blue dot in the image, or also in optical images of chlorophyll A concentration. So SWOT really allows to observe a structure which are less than 10 kilometers, and this is really a game changer for altimetry. Another limit of altimetry, however, is that geostrophy is not everything. We calculate geostrophic currents from altimetry using this assumption, which is very, very good, but there are many other currents at shorter scales or different time scales also, which diverge from altimetry. The main currents are the Ekman currents. This was discovered by Ekman in 1902. It's due to the wind, and when the wind is blowing at the surface, it will create a current that deviates from 45 degrees at the surface and rotates at depth. And will be proportional to the wind speed. When the wind stops blowing, actually the water parcel, they won't stop immediately. They're still influenced by the Coriolis force, so due to the Earth's rotation, and so they will do oscillations. And so this is the top right example. We have this inertial oscillation. We have the Stokes drift that Lofty was mentioning before, which is due to the fact that there is a net transport in the wave direction of the particle of water at the surface due to the waves. And the current that all of you know when you were on the beach, so the tidal currents. So all these currents are not in geostrophic equilibrium, and we cannot see them from altimetry. To see them, we rely on a very important observing system, which is now active since several decades, which is made of drifting buoys. So these are in situ measurements made of a surface float, which is transported by the currents, with a Holy-Sock drag that makes it drift by the currents at 15 meters. And you see the status of this global drifter array on the top right figure. So it's today 1,273 buoys on the world. The position of the drifter is transmitted via satellite. And so from this position, we are able to calculate currents. And the drifter, of course, is transported by all the currents, so the geostrophy, the Ekman, the tides, everything. So this is a very important information to estimate surface currents. And this is the mean currents that you can derive by averaging over a very long period this information, and you can recognize actually the general circulation I was mentioning before. Of course, these are in situ measurements. You can have a nice average view of these currents, but they are not depicting the ocean currents everywhere, every minute. So for that, we need to combine with a satellite again. And so this is, I will go very quickly. It's, I show the equation just to mention that these Ekman currents, they can be simply estimating by the knowledge of the wind stress and by estimating some simple parameters, R parameters of the amplitude of the current and the direction to the wind of the current. And these two parameters can really be estimated by merging the information from the drifters and from the altimetry. And you can see on the bottom middle plot what we get on a given day using the wind information and this very simple model for Ekman currents that can be added to the geostrophic currents derived from altimetry to get a more complete view of the surface current, the geostrophy plus Ekman. So here is an example why this can be, this is very important. You all have heard about the giant plastic island that form in the middle of the ocean. And this is an animation that is created by Victor Honing using these total currents from altimetry and Ekman that I was explaining before. So you can imagine that each red dot is a piece of plastic in the ocean, and you use this current product to make this dot be transported by the current during many months, many years. There is an animation which does not start. This is bad. You would see each particle being advected and being converging in the center of the ocean, and you would end up with this type of concentration. So by the total, the geostrophic plus Ekman currents. This slide is to show that if you use only the geostrophic component, so you don't add Ekman to it, and you do the same simulation, you would end up with this distribution. So it's to show that this is really due to the fact that we need not only the altimeter geostrophic current, but also the wind-driven currents to explain what we actually see in the ocean. There is another sensor beyond altimetry that is very useful for estimating ocean current, and this is a synthetic aperture radar on board the Sentinel-1 mission. Also here there is an animation, but it does not work. Oh yes, okay. And so this is a sensor that sends a signal. It's an active sensor. It sends a signal toward the ocean, and it measures the backscattered signal. It sends a signal with a given frequency, and it uses the Doppler shift to estimate the currents. So how does it work? You all have experienced the Doppler shift, which is the fact that when you have, for instance, an ambulance coming toward you, you will hear a higher pitch, a sound with a higher pitch than when the ambulance is going away from you. So this is what we call the Doppler shift. And when the satellite Sentinel-1 sends a signal toward the surface, and it is backscattered by water particles that are moving toward the satellite because of currents which moves towards, the frequency of the signal will be slightly changed. It will be higher, and it will be lower if the particle is moving away from the satellite because of the currents. So by analyzing this difference in frequency, we can go back to the current. The problem of this, methodology is that you have only one component of the current, the component which is perpendicular to the satellite track. If you want to get the other components, you need more satellite. You need to have a different direction so that you can reconstruct the full current. And this is actually the principle behind a future mission that we have in ESA called Harmony, Earth Explorer number 10, which will be able to map ocean currents at 2 to 5 kilometer resolution using this approach. And my last slide, I come back to the thermohaline circulation I was mentioning at the beginning, which is a 3D movement of the water. And of course, one limitation of satellite also is that we are seeing the surface and we don't see the depth. And this thermohaline circulation is mainly driven by density changes. So we rely on another very important observing system, which are the Argo profiling floats, which drift in the ocean and dive at depths and measure temperature and salinity profiles, which are then transmitted to satellite. And from this information, so temperature and salinity at depths, combined with altimetry at the surface, using complex equations, we are able to reconstruct the 3D geostrophic current fields. Okay, main messages. Ocean currents are very important for a wide range of applications. Again, today we have no satellite that measures directly the current, and altimetry has been by far the most used instrument for surface current monitoring. But it has important limitation. It sees only one component of the current, the geostrophic, and it has also limit in space and time resolution. SWOT altimetry is a game changer, but again, it's only about geostrophy. So we need to use altimetry in synergy with other measurement, temperature, in situ data, to retrieve ocean currents both at the surface and at depth. And future mission will help bridge this gap and improve the retrieval of this crucial information. Thank you.
Thank you. Thank you, Marie-Hélène. So you see that measuring surface current from space is tricky, and we have a dream oceanographers have a dream is to have a mission that is able to measure ocean current from space, and it will come soon to reality.